Hello once more. Now let's recall the previous lessons under waves. In the two previous lessons, we talked about what actually a wave is, the energy a wave produces as it travels, how a wave actually travels, what happens to the particles of a medium and the medium itself when a wave travels. Also, we talked about the categories of waves, under which we saw electromagnetic waves and mechanical waves. And under electromagnetic waves, we said electromagnetic waves are those that can actually travel through space. And we went on to say mechanical waves are those waves that cannot travel through space. They need a medium to travel through. Now, about the energy transfer when a wave travels, we said when a wave travels, it transfers energy from one point to the next, and that the particles of a medium together with the medium do not change their positions to a new position when a wave passes through. The only thing they can experience is steady oscillations or vibrations. Now, under electromagnetic waves, we saw the different examples, which were radio waves, microwaves, X-rays, gamma rays, visible light, infrared. And under mechanical waves, we saw that mechanical waves can still be classified under two types, which are longitudinal waves and transverse waves. Now, we said transverse waves are those waves that travel in a direction perpendicular to the direction of travel of the disturbance. Meanwhile, longitudinal waves are those waves that travel in the direction that is the same as the direction of travel of the disturbance. We went ahead to give examples of transverse waves, which were water waves and waves produced by oscillating springs. While examples of longitudinal waves were sound waves and waves produced by a compressing spring. Now, in this lesson, we shall be talking about the different terms frequently used in waves, that is, associated terminology. There are terms that we always come across when dealing with waves. If you can remember, under transverse waves, we saw that transverse waves have crests and troughs. Those are examples of the terms that always appear under waves. We also have terms like frequency, amplitude, period, and wavelength. Now let's take the crest. What actually do you think a crest is? If you remember the propagation of transverse waves, what definition can you give for a crest? A crest is the highest point on a wave. That is, the highest point a wave makes is what we call a crest. And a trough is the opposite of it. That is the lowest point on a wave. Now, what do you think wavelength is? is the distance between any two corresponding points on a wave, like the distance between one crest and the next crest, or the distance between one trough and the next trough, or the distance between one compression and the next compression, or the distance between one expansion and the next expansion. Now take a look at the figure in front of you, figure 1. You can see the crest, which is the maximum position of the wave. That is the maximum point of the wave. There is no other point on this wave that is higher than the point. And now for the trough is the minimum position, the minimum point of the wave. No other point is below this trough. And now, the distance between one crest and the other, as can be clearly seen on the figure, gives you the wavelength. This is still the same as the distance from one trough to the other. Amplitude, as can be seen on it, is the maximum displacement of the wave, as we shall see in the next slides. So, the crest of a wave is the maximum position of the wave. The trough is the minimum position of the wave, and the wavelength is the distance between two corresponding points, like the distance between two crests or the distance between two troughs. Taking period. What is the period of a wave? The period is the time needed to make one complete oscillation. It is the time needed to make one complete oscillation or vibration. Frequency. Frequency is the number of complete oscillations made per second. The number of complete oscillations made per second is what we call the frequency of a wave. Meaning, if a wave makes 50 oscillations in 1 second, then the frequency of that wave is 50. But if a wave uses 1 second to make one complete oscillation, then the period of the wave is 1. So the period of a wave is the inverse of the frequency of a wave. Going to velocity. From the previous knowledge, you must have heard of velocity in Form 2, in Form 3. Velocity is the displacement of a point on the wave, and its units is in meters per second. Talking about amplitude, like I said before, amplitude is the maximum displacement of a particle from its initial position. That is, its maximum displacement from the equilibrium, from where it was initially. So the maximum displacement of a particle from its equilibrium position is what we call the amplitude the particle. Now, amplitude and energy are related. The amplitude and the amount of energy carried by a wave are related in that a high energy wave has a high amplitude and a low energy wave has a low amplitude. This is to say, any wave that has low amplitude also has low energy, and any wave that has high amplitude also has high energy. Now take a look at the two figures in front of you, figure 2 and figure 3. In figure 2, you can see that the displacement of the wave from the equilibrium position is lower than the displacement of the wave from the equilibrium position in figure 3. That is to say, figure 2 has a low amplitude than figure 3. And this low amplitude results to low energy. So a wave with a low amplitude is a wave that has low energy, as shown in figure 2. And a wave of high amplitude is a wave that has high energy, as shown in figure 3. So generally, any wave that has a very high energy produces high amplitude. That is, it will be displaced to a very high position from the equilibrium position. But a wave with a low energy will also have a low amplitude, meaning its displacement from the equilibrium position will be low. So amplitude is directly proportional to the energy. The amplitude of the wave is directly proportional to the energy of the wave. Low amplitude gives low energy, high amplitude gives high energy. It's the same thing that is shown to you in the figure 4. In the first diagram of figure 4, you can see it written there, more energy. That is because the amplitude is high. That is, the point at which the wave is from the equilibrium position is higher as compared to figure 2. In the other one, as written, less energy, the amplitude is lower because of lower energy. So this gives a clear distinction of how amplitude is related to energy. High energy equals high amplitude, and low energy equals low amplitude. Talking about the phase of a wave. When we say two waves are in phase, what it means is that the two waves are traveling in the same direction at the same time. But two waves that are out of phase mean the two waves are traveling in different directions at the same time. This means particles that are exactly at the same position at the same time, traveling in the same direction, are in phase. Meanwhile, particles that are traveling in opposite directions at the same time are out of phase. Now, when two waves are in phase, they can be combined to give a single wave, as seen in figure 5 in the next slide. Meanwhile, two waves that are out of phase, they combine to give a straight line. Take a look at the two figures in front of you, figure 5 and figure 6. Figure 5 shows how two waves in phase combine to give one wave. Meanwhile, figure 6 differentiates them. Two waves in phase combine to give one wave. In the first part, the second part, the two waves out of phase combine to give a straight line, while the third part, the two different waves out of phase totally combine to give a different wave. As seen in figure 5, when two waves in phase combine, they give one wave with a greater amplitude. The amplitude of the resultant wave is greater than the amplitude of the individual waves before they combined. But two waves out of phase, when they combine, the resultant is a straight line. They combine to give a straight line. This is to say, their total amplitudes are reduced to 0. But two different waves traveling in different directions combine to give a different wave. This clearly differentiates between waves in phase and waves out of phase. So waves in phase travel in the same direction at the same time, and when they combine, they give a wave of greater amplitude. But waves out of phase travel in opposite directions at the same time, and they combine to give a straight line. In the figure displayed in front of you, points A prime, A prime prime, and A prime 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 are all in phase because at the same position they are traveling towards the same direction at the same time. It's the same thing with points B, B prime prime, and B prime prime prime. But point A is totally out of phase with point B prime. Point A is totally out of phase with point B prime prime. Point A is totally out of phase with point B prime prime prime. So generally, point A prime prime, A prime prime prime, and A prime 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 are all in phase, traveling in the same direction at the same time. Same with point B prime, B prime prime, B prime prime prime. But point A prime is out of phase with all points B prime, B prime prime, and B prime prime prime. And point B prime 2 is out of phase with all points A prime, A prime prime, A prime prime prime, and A prime 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 prime. This brings us to the end of our lesson. In In the next lesson, we shall talk about the wave equation.